Okay, Assalamualaikum everyone and a very good day. So today we are going to discuss about experiment 1, shapes of molecule, that being held on 18 March of 2024. We are from group A9, me, myself, Irdina, Asmira and also Vinesh. So the objective of this experiment is to write the Lewis structures of molecules and to apply basic aspect of bonding to molecules. The second one, to predict and to visualize base structures of the molecules. Okay, so for introduction, in this experiment, Lewis structures of molecules are constructed by representing valence electrons as dots around the symbols of surrounding atoms, which is hydrogen or halogens, and the central atom. So the central atom's valence electron dots are positioned opposite each other or at the corners of polygons depending on the number of valence electrons. Covalent bonds are formed between unpaired electrons of surrounding atoms and the central atom, which are represented by short lines. For the electron pairs on the central atom, it is identified by the remaining valence electrons. So molecular models are built using plastic centers to represent atoms and prong sets to depict the bond angles. So the geometry of molecules is determined by minimizing electrostatic repulsion between bonds and lone pairs with linear, trigonoplanar, tetrahedral, trigonobipyramidal, and octahedral geometries occurring for central atoms with 2 to 6 single bonds, respectively. So the lone pairs can distort these geometries, leading to band shape, trigonopyramidal, distorted tetrahedral or seesaw shape, T-shape, square pyramidal, and square planar structures. So as for materials, we use 6 pieces of 5 centimeters plastic straws, cotton thread, a ruler, a protector, 6 pieces plastic centers with a prong, white color, and plastic centers with 2 straight prongs, 1 piece of 3 prongs, 1 piece of 4 prongs, 1 piece of 5 prongs, 1 piece of 6 prongs, which all of them have different colors.
First part, we are going to construct a molecule which have central atom with 2 electron domains, which is the beryllium hydride. This molecule carries the chemical formula of BeH2 and the Lewis structure is as shown. So the materials that we are going to use are the 2-piece 5 centimeter plastic straw, which acts as the link bridge between the beryllium atom and the hydrogen atom. Then we are going to use a 1-piece 2 prong, which acts as the beryllium atom. Then we are going to use 2 pieces of 1 prong, which acts as the hydrogen atom. So the shape of this atom is linear and the molecule has an angle of 180 degrees. So as per discussion, all angles are approximately equal to each other, which is 180 degrees. The shape that is predicted for the beryllium hydride molecule is a linear shape.
So for molecules having central atom with 3 electron domains, so for example, boron trifluoride, BF3. So as you can see on the slide, Lewis structure for boron trifluoride, boron as a central atom and fluoride as electron domains. So for the materials, we're going to do 3 pieces 5 cm plastic straw as a link bridge, and 1 pieces 3 prong as a boron atom, 3 pieces 1 prong fluorine atom. So for the next slide, there's a video of how we construct the trigonoplanar shape, and on the slide you can see molecule model. So for the next slide, there's a video of. So next for discussion, we measure the shape. We measure the boron trifluoride and we got 120 degrees, and all angles are approximately equal to each other, which is 120 degrees, and the shape formed by the cotton thread is a trigonoplanar shape, as you can see. For 2.2, which is tin dichloride, SnSCl2. So on the slide we present the Lewis structure, Sn as a central atom and chloride as a electron domains. So it has a band shape, and for the molecule model you can see on the slide, and Sn as 1 lone pair.
For this part, we are going to construct a molecule which has central atom with 4 electron domains. So this molecule is methane, which carries the chemical formula of CH4, and the Lewis structure is as shown. The materials that are going to use are 4 pieces of 5 centimeter plastic straw, which acts as the link bridge, 1 piece 4 prong, which acts as the carbon atom, and 4 pieces 1 prong, which acts as the hydrogen atom. So the shape formed by the thread is a tetrahedral, and based on the molecule model, we know that the angle of the molecule is 109.5 degrees. So the shape formed by the thread is a tetrahedral, and based on the molecule model, we know that the angle of the molecule is 109.5 degrees. So the shape formed by so as per discussion, all angles are approximately equal to each other, and the shape formed is a tetrahedral shape. The next molecule that we can build, which has a central atom of 4 electron domains, is ammonia, which has the chemical formula of NH3. The Lewis structure is as follows. Ammonia has 1 lone pair, and the shape formed is a tetrahedral band shape, and it has a 107.8 degrees. Another molecule that we can build, which has a central atom with 4 electron domains, is water, or else with the chemical formula H2O. The Lewis structure is as follows. Water has 2 lone pairs, and it carries a tetrahedral V shape. Water, or H2O, has an angle of 104.5 degree.
So we can see from the video is how we constructed our phosphorus pentafluoride model, which then will form the shape of trigonal bipyramidal. So in the molecule model, we can see that there is an intermediate angle, bond angle with 120 degree, and the smallest bond angle with 90 degree. So we can see from the video is how we constructed our phosphorus pentafluoride model, which then will form the shape of trigonal bipyramidal. So in the molecule model, we can see that there is an intermediate angle, bond angle with 100. So as for our discussion, the shape formed by the cotton thread is a trigonal bipyramidal, and there is 3 of intermediate bond angle with 120 degree, and there is 3 of the smallest bond angle with 90 degree. So the fluorine atom with the red highlighted bond is the axial phosphorus fluorine bond, and there is the 3 remaining with the yellow highlighted fluorine bond are the equatorial phosphorus fluorine bonds. So the second molecules that have central atom with 5 electron domains is sulfur tetafluoride or SFO. So in the diagram, we can see the Lewis structure of SFO, which contain of 1 sulfur as the central atom, 4 fluorine atom as the electron domains, and 1 piece of lone pair. So as the first model, we can see that there is 3 sulfur fluorine bonds that are perpendicular to the electron pair on the sulfur atom. While the second model, we have 2 sulfur fluorine bonds that are perpendicular to the electron pair on the sulfur atom. As for discussion part, the question asks about what is the angle between adjacent lone pair of electron. So the angle between the lone pair and the other one between the central atom and electron domain is 90 degree. For the second one, in terms of electrostatic repulsion, the lone pair in which models of the sulfur tetrafluoride experience more repulsion. So the lone pair in the first model experience the most electrostatic repulsion since it has more sulfur fluorine bonds that are perpendicular to the electron pair on the sulfur atom, which is 3 sulfur fluorine bonds. So question number 3 asks which model will be chosen as a suitable sulfur tetrafluoride molecule. So we know it will be the second model since it is the stable molecule which is in seesaw shape because it has the less sulfur fluorine bonds that are perpendicular to electron pair on the sulfur atom. So the name of this particular shape is called as trigonal bipyramidal.
Another molecule that has a central atom with 5 electron domains is a chlorine trifluoride, which carries the chemical formula of ClF3. The Lewis structure is as follows. In this diagram, 2 lone pairs are 90 degrees to each other, and chlorine trifluoride certainly won't take up the shape because of the strong lone pair repulsion. So, the most stable chlorine trifluoride structure as in the molecule model drawn will be discussed in our discussion. As per discussion, the first question is, what is the angle between adjacent lone pair of electron? The angle between the lone pair and the other bond between the central atom and electron domain is less than 120 degrees. The second question, why the electrostatic repulsion can be ignored? The bond to the fluorine in the plane is at 90 degrees to the bonds above and below the plane. So there are a total of 2 bond pair repulsions. That makes a total of 4 lone pair bond pair repulsions. The other fluorine, which is the one in the plane, is 120 degrees away and feels negligible repulsion from the lone pairs. The structure with the minimum amount of repulsion is described as T-shape because bond pair repulsion is less than lone pair bond pair repulsion. Number 3, the name of the shape. The name of the shape is trigonal bipyramidal, or we can say a T-shaped chlorine trifluoride.
So for the fourth molecules that have central atom with 5 electron domains, we have xanthine difluoride, which is XeF2. So the Lewis structure is shown in the picture, and there is a molecule model drawn, which is presented in the slide. And there is the model that we have built during our experiment. So for our discussion part, the molecule model of xanthine difluoride created during the experiment is actually considered unstable because when 2 lone pairs are placed in the equatorial positions and the third lone pair is in the axial position, in a molecule like xanthine difluoride, it actually will result in an unstable configuration due to increase in electron-electron repulsion. So this arrangement creates greater repulsion between the lone pairs as they are closer together in the equatorial plane, leading to higher energy, which decreases stability compared to a configuration where lone pairs are more evenly distributed. Hence, the most stable shape of xanthine difluoride model is the linear shape as shown in the diagram beside. So the linear shape of xanthine difluoride is considered as the most stable due to its maximal symmetry, minimal electron pair repulsion, and effective utilization of atomic orbitals, which contribute to the molecule's overall energy minimization.
Molecules having central atom with 6 electron domains. So we got sulfur SFO right here, SF6. So for the Lewis structure, you can see on the image on the slide. So for the material, we're going to use 6 pieces 5 cm plastic straw as a Berlin bridge, 1 piece 6 prong as a sulfur atom, 6 pieces 1 prong as a fluorine atom.
So in the video, we can see that we are constructing the sulfur hexafluoride molecule, which will form a shape of octahedral. And beside it, we can see the molecule model that has been drawn, which having the angle of 90 degree. So in the video, we can see that we are constructing the sulfur hexafluoride molecule, which will form a shape of octahedral.
So for discussion, the shape by the cotton thread is octahedral, The bond angles in octahedral geometry are 90 degrees with the injection atom. But in SFC, all bond angles are 90 degrees. There's no variation in in the bond angles as they are the same in this symmetry arrangement. And there are three pairs of 180 degrees between the pair of fluorine bond that lies in the straight line. There are three pairs of sulfur fluorine bond which lies in the straight line, and the pair of SF bond that lies in the straight line you can see on the slide. They are named as axial bond pair, and the remaining pair of SF bond that lies in the straight line, we can name as equatorial bond pair.
So for the second molecules having central atom with 6 electron domains, we have bromine pentafluoride. As we can see in the Lewis structure, the bromine central atom has bonded with 5 fluorine electron domain, and also we have 1 lone pair. So the molecule model constructed is based on our model that has been created during the experiment. So the shape formed here is tetrahedral, which is square pyramidal shape.
Another molecule that we can build, which has a central atom with 6 electron domains, is a xenon tetrafluoride, which carries the chemical formula of XeF4. The Lewis structure is as follows. Xenon tetrafluoride has 2 lone pairs. We have built 2 models as per discussion. Both the first and second model have an angle of 90 degrees between the lone pairs with the same seesaw shape. However, xenon tetrafluoride does not exhibit a seesaw shape. This is due to the presence of 4 bonding pairs and 2 lone pairs of electrons around the central xenon atom. In a seesaw shape, there would be 5 electron pairs around the central atom, which is not the case for xenon tetrafluoride. Therefore, the lone pairs are positioned in equatorial positions to minimize repulsion, resulting in a square planar shape as shown in the diagram beside. This arrangement allows for the maximum separation between the lone pairs and the bonding pairs, leading to a stable kilo structure. Each model of xenon tetrafluoride is a square planar shape.